lovely people, welcome back to my series on rocks and minerals. If this is the first time that you've joined us, well, welcome, and welcome back to those who have seen the first two episodes. My name is Roxanne and I'm here to talk about rocks and minerals and to help students and anyone interested in understanding the world of rocks and minerals. So in the first episode I talked about a general overview of what rocks and minerals were, and in the second video I defined what minerals were and what a rock was, and I gave you examples of what those two were. And I think from memory I mentioned something about at the end of that video in my next one talking about the different classifications of rocks and minerals, and today we're going to talk about how minerals are classified. Broadly speaking, minerals are classified into two broad groups, either rock-forming minerals or ore-forming minerals. And this is particularly important because one is more based on the petrology of the world around us that we see, and the other one's a little bit more economic. So we have two entirely separate groups of minerals here, even though two minerals in one specimen technically defines a rock. Once they're classified into their different subgroups, they tend to be defined as an ore, not necessarily a rock. Whereas rock-forming minerals, we tend to always talk about them in reference to rocks. So we don't tend to be looking at silicates and quartz as an ore, we tend to be looking at more like a zinc sulfide, a sphalerite for example, or an iron sulfide, a pyrite as an ore, and that's quite economically important. So these are the reasons why we talk about the two different types of minerals. There are loads of different ways that we can categorize minerals. We can classify them according to their chemistry, according to their internal mineral structure. We can talk about where they're found, or we can talk about what the importance of the mineral actually is. We could classify them according to colour if that's what we were learning to do. We could classify them according to their specific gravity. All those properties we can use as a classification, but we tend to use these two main broad categories of rock-forming minerals and ore-forming minerals, largely so that we can understand what we're looking at and why we're looking at it. Today we're going to be talking, as I said, about ore-forming minerals. With the rock-forming minerals, they're mostly silicates. So we're talking about minerals like quartz, feldspars, micas, pyroxenes, amphiboles, and olivines. Then we have associate minerals like accessory minerals like kyanites and garnets and things like that. So they're all silicates. If you notice, there's something very common with all of those rock-forming minerals, they're all silicates. When it comes to ore-forming minerals, they tend to be of a completely different group altogether. They tend to be things like oxides, sulfides, sulfates, and carbonates. So I'm going to today give you an example of how we can have the one same set of minerals and we're going to classify them completely differently. And the two primary ways that we're going to be doing that is based on the ore that they are, whether they're a zinc, lead, copper or iron, or whether they are an oxide, sulfide or a carbonate. So let's have a look at those. We're going to start the demonstration of our minerals today looking at sulfides. We're going to start with looking at an iron sulfide, a zinc sulfide and a lead sulfide, and in a couple of different forms. This one here is actually a copper iron sulfide. So we'll start off with the most spectacular piece, which everyone always thinks is a manufactured polished piece. This is pyrite, and this is its natural cubic form. Now, two of these sulfides actually take a cubic form. Both the galena and the pyrite take a cubic form. So they're simple heavy metal sulfides. They take this enormous cube here, and people think it's synthetic, but it's not. It's actually a natural formed one. And you can see in this little piece, it's taken its cubic form as well, but this little corner is where it was probably anchored into the bedrock that it was taken from. So that is iron sulfide, pyrite. When you take iron sulfide, but you add a little bit of copper to it, the crystal becomes amorphous. It loses the bright goldy colour and the solid gold colour, and it starts to become more of a peacock coloured ore. And this is actually literally what they used to call peacock ore. So, and that's a copper iron sulfide. So when they were doing fossicking and they were looking for ore deposits, they were looking for rocks that were exposed on the surface that had this sort of peacock coloured tinge to it, and they knew that they were probably quite close to some kind of copper iron ore lode somewhere. And this little piece here is just another form of pyrite. but it also has galena on the other side, and these minerals often form together in the same lode. That's LODE. That means the deposit of mineral that was actually found. So then we move on to sphalerite. Sphalerite is a zinc sulfide, and this is also quite a spectacular piece. This one does come from overseas, it's not from the Broken Hill. I have a few Broken Hill pieces of sphalerite. Broken Hill, by the way, was an enormous mine to find. Some of the best specimens in the entire world of these iron ores, copper ores, lead, zinc, a whole range of minerals actually come from Broken Hill. The most spectacular specimens in the world's museums come from Broken Hill, but this one does come from overseas. Now this is sphalerite, it's a zinc sulfide, and you can see that it's taken more of a rhomboidal form. It is nonetheless quite a spectacular piece. I have other pieces of sphalerite, not quite as spectacular as that one, but sphalerite will take on quite a vitreous luster. It will be quite grey in colour and look fairly unappealing in many pieces that you hold in your hand, but this just happens to be quite a brilliant piece. I'm quite pleased with that one. And the last one we've got here is galena. Now galena is lead sulfide, and it too, like the pyrite, is cubic. And this has got rhodochrosite on the other side, which is a really pretty pink mineral. But on the other side, you can see here it's taken on quite a very clear cubic facet. And we refer to this as perfect cleavage. So these are forming not just in cube shapes, but when you actually break it and fracture the mineral sample itself, it will break and fracture into these exact planes. If we were to break this piece of pyrite, it will cleave on those perfect planes as well. So, and we call this as having, we'll do this in another episode, but just quickly we call it as having an X, Y and a Z axis. So top, bottom, sides and back and front, it's all perfectly flat. So that means, and they're all at 90-degree angles, and that's the definition of a cube. So they take on this cubic shape. And you can see this little piece here as well. This is galena as well. And even if you look at it really, really close up, you can see that it too will fracture or has fractured in those cubic planes. So that's the three basic minerals that I've got there for today. Well, actually four if you take into account chalcopyrite. So these are the basic sulfide ores that they're looking for under exploration. And this is one of my newly acquired pieces, and this is a piece that's got all four of them in it. It does actually have sphalerite, pyrite, galena and chalcopyrite all in the same piece. Let's move on to oxides. See you in a sec. So now we're going to quickly talk about oxides. I've just got a couple of examples of oxides. We've got botryoidal hematite, which is a simple iron oxide. We have got another iron oxide, which is called magnetite, and we've got tin oxide, which is called cassiterite. Now again, these are also very simple chemical formulas. So let's start off with the basic iron oxide. So this iron oxide, Fe2O3, is in the formation of a botryoidal shape. Now, even though this is an iron oxide as well, it's called magnetite for one really simple reason. Look at that. It's magnetic. So the chemical composition for hematite was Fe2O3. Magnetite is Fe3O4. So one extra iron and one extra oxygen makes it magnetic. It turned it from this, which is not magnetic. This is Fe2O3. This is hematite. And then this is magnetite, just in the same molecule, but with one extra iron, one extra oxygen, and it makes it all magnetic. Look at that, really cool. Now the last one that we have is cassiterite. And it's not magnetic, as you can see. It has, again, lovely flat crystal faces on different sides. It will come in anything from, I've seen cassiterite as small as the little tip of your pen to these nice crystal formed pieces here. So it's not very common to find cassiterite in much larger pieces than that, but nonetheless a very important ore. And it's when they start finding these minerals that they know that they're really close to iron. Let's move on to one more group, the carbonates. Okay, and now we're going to look at carbonates. What a pretty amazing group of minerals these are. I mean, just look at them. Look at the stunning brilliance on these. Isn't that incredible? And to think, these are all from the same family of minerals. These are all carbonates. So let's go through them one at a time. Two of these things have a lot in common in particular, and that is these two. This is azurite and malachite, and you can see where the words have come from, can't you? So these are both copper carbonates. Now one's got an extra molecule in it, and that's what gives you the extra colour, but one morphs into the other over time. So you can see this concentric banding. This is malachite in a botryoidal form. Now in the middle there is also a lead carbonate called cerussite. So that's another lead carbonate mineral as well. This one comes from Rum Jungle in the Northern Territory. Quite a beautiful piece. And this too is a beautiful crystalline botryoidal form of azurite. And you can see it has tiny, tiny little micro crystals on the top of them. So malachite and azurite can actually come in different forms, and they can come in some very, very beautiful coloured crystal forms from these botryoidal amorphous banded forms, or they can come in some beautiful, beautiful crystal prisms. They're quite rare. Those ones are quite rare. I don't have a sample of that yet. I've got one coming, but for now that's all we need to see. So here, this one's called smithsonite, and this one comes from Dundas in Tasmania. So this is a zinc carbonate, and they form these tiny little crystalline bubbles, which is a very simple zinc carbonate. And they can come in a variety of colours depending on if there's other impurities in them. Turn it around, have a look onto the other side. You can see concentric bands there. You can see that this was a hydrothermal fluid of some kind, and it crystallised out throughout the gaps into the rock. That's how most of these minerals form. Now we have an iron carbonate called siderite, and this one quite brilliant in its lustre, and it has an oblique angle. It has a 90-degree on both the X and the Y axis, but it is oblique onto the Z axis. So that's what forms these kind of cubic but kind of bladed crystals. And this one actually has quartz. This is siderite with quartz. So that's a carbonate. And then this one, we can't go past a carbonate without talking about calcite, pure calcium carbonate. This is not completely pure calcium carbonate because it has colourings in it, which means it's got some impurities in it. But calcium carbonate, that will definitely fizz in hydrochloric acid. That's a very strong characteristic of a calcium carbonate. And you can see that it has fracture lines along its own cleavage faces. We're not talking too much about just yet about these particular properties like cleavage and fracture planes and crystal structure and whatnot, but just to know that all these minerals have their own different form and habit, that just because it's a carbonate doesn't mean to say it's going to look the same. So it's really important to understand that just because an element can be in different form, they're going to look completely different. Okay, just to recap, remember this was the group of minerals that we've looked at today. Remember how I said that there was two possible ways that we could classify the same set of minerals. We can classify them according to their elements, whether they were an iron, lead, zinc or copper, or we could classify them according to their chemistry, whether they were an oxide, a sulfide or a carbonate. So let's start with the elements first. Let's start off with iron. So here we've got, remember, hematite, iron oxide. Put this in a row at the top. So we've got hematite, that's one iron oxide. We have a second iron oxide, which was magnetite. So that's another iron mineral. We have pyrite, which is an iron sulfide. And we have siderite, which is an iron carbonate. So that's our iron row at the top. Let's look at the zinc minerals. Which ones were the zinc? So we have the zinc carbonate, which is smithsonite. We have the zinc sulfide, which is sphalerite. And there we go. And then that leaves our lead minerals. So lead, we've actually got galena, which is a lead sulfide. We've got that white mineral in the middle, even though it's with malachite, that's the lead carbonate, so that's in there. So even though it's mixed up, we'll put that one there. We've got iron, zinc, lead, and one more row, we can squeeze them in. Let's go copper. So we go one form of copper carbonate, another form of copper carbonate, azurite, malachite, and again we've got a copper mineral, which is a copper sulfide. There we go. So let's organise it differently. Let's organise it according to its chemistry. Let's put oxides down this row, shall we? Well, that doesn't belong there because that's the carbonate. We'll start off with the hematite because that's an oxide. So we'll put the other iron oxide in front of it, which is the magnetite. Put you there. So there are oxides. So let's, in this row, put sulfides. We've got iron sulfide next to the iron oxide. We have zinc sulfide, sphalerite. We've got lead sulfide, and we've got copper iron sulfide, which is a chalcopyrite. So that's our sulfide row. So we've got our oxide row and we've got our sulfide row. Oh, there is one more oxide, tin oxide. There we go, cassiterite. Let's look at carbonates. One more row now. Our lead carbonate, that one goes there next to that lead one. This one is a zinc carbonate, so we'll put you down at the front. We've got a copper carbonate here, malachite, and another copper carbonate right there, azurite. So there you have it. We've arranged this group of 12 minerals into 3 different groups. So we've first of all arranged them according to their element, and then we've classified them according to their chemical formula. In this row we've got oxides, sulfides, and carbonates. So that is just one way that we can rearrange all these minerals, and this is a way for me to be able to show you and communicate to you that a mineral is classified according to how we actually want to see the mineral. So thank you for joining me. It's been great fun. I hope you enjoyed it and learnt something too, and I'll see you next time. Bye.